Good afternoon, everyone. I'm Annie Johnson, and I'll be presenting my capstone exploring trust and strategies in agent-human teaming. And my work is with Professor John Stamper. So let me first introduce to you the realm of agent-human teaming. So with the advent of more and more AI agents being deployed in real-world applications like chatbots and autonomous vehicles, um, researchers have shifted their focus from developing better performing models to actually investigating the relationship between humans and AI agents and trying to figure out their weaknesses and strengths. So in this particular project, the goal is to define and evaluate trust in human AI collaboration. And for this, we use a gaming platform. And the game that we use is called Overcooked. So quick overview of the game. It's a timed game where there are two players who have to collaborate and make as many soups as they can to score more points. So there are three different types of agents that we've experimented with in the project, which consists of the self-play agent, which is an agent that has a very fixed or static strategy such that each player can play the game independently and does not really rely on collaborating. The human-aware agent, on the other hand, tries to understand the strategy that is employed by the other player and then complement that other player. And the population-based agent also has a static strategy, but it is a strategy that's more efficient and collaborative than the self-play agent. Coming to the formal research question that we're addressing, the question that we're addressing is what aspects of the game or agents actually influence trust in human players? Or as a constructive hypothesis, we could put this as, is it possible to identify strategies and develop a model that can detect factors that affect trust and collaboration in the game? So we've been throwing this word trust around quite a few times. So let me define what trust is in this scenario. So we know in the game there are two players, an agent and a human. So the human player can take two roles. One could be that of a leader or of a follower. So what do we mean by a leader? A leader is one that formulates its own strategy and expects the follower to understand its strategy, that is the agent to understand its strategy and accordingly complement it. And a follower is a human player who tries to understand the strategy of the agent and tries to complement that. So these are the two different roles that a human player can take. So formally put, trust refers to evaluating whether human players prefer to follow an AI agent. In this case, we'd say trust exists because the human player is convinced that the AI agent has a robust strategy and that the human player can complement it. And if the human player prefers to lead, then we would say the trust does not exist in that scenario. Strategies just refer to the series of steps or actions taken by either of the players. So in order to address this particular research problem, we come up with a three-phased solution. So in the first phase, we plan to conduct a HCI study to address the particular research question. So in this, we recruited participants to come play the game and answer survey questions based on their gaming experience. In the second phase, so in the first phase, we also collect data that we use in the second phase. So in the second phase, we have two tasks. One is to use an AutoML model to perform object recognition to evaluate the robustness of the entire game. And for this, we use the recordings that were collected in the first phase. And the second task is to use an unsupervised neural network called self-organizing maps to visualize features in the data to understand like which features are actually promoting score and trust. In the final phase, we basically combine the analysis that we get from phase 1 and phase 2 and summarize the final takeaways. Coming to the intended users, so as human-agent collaboration is extending to other domains, researchers and engineers who work in these domains would be the intended users of this research because they would be able to look at this research and take it forward to these other domains. There are three non-functional requirements that we try to tackle throughout the research project. These are availability, performance, and usability. So as this is more of a research-oriented project rather than a software application, we try to make sure that the protocol that was developed during the HCI study and all of the analysis that was done during the analytics phase, everything has been publicly available on GitHub so that it can be easily downloaded by anyone to recreate a similar experiment. And because it's publicly available and easily uh, uh, as anyone can redo the experiments, it also promotes usability. And in the results section, the performance can be seen like for the object recognition module and the SOMs that are created. So we can see that there is a good performance on the data that we've collected. Coming to the overall system architecture, this purple component here is the HCI component. So here, in this section, we did the literature survey and we formulated the research questions. And initially, we were planning to do this as an IRB study. And so we had to get conduct certificates and apply for IRB. But however, due to some challenges, we weren't able to do this as an IRB study. So we just did it as a HCI study. And then once the study was done, we got three different kinds of data. That is the survey data, the recordings, and the trajectory data. These green boxes indicate the second phase or the analytics phase. And the recordings, the video recordings were used in the object recognizer module, where the MP4 videos were spliced into image frames and stored in and annotated based on the various components that were present in each image. And it was stored on cloud storage, and the Vision API was used to train and deploy object recognizer. And in this second box, the trajectory data, which is also obtained from each gameplay, and it is in JSON format, that was used, that was pre-processed, and follower and leader patterns or strategies were identified, and these were translated into features, and these features were used to visualize using a self-organizing. Finally, all of the inferences that we obtained from the HCI component and the analytics component and the survey data that we got was used to provide the analysis and conclusion in the third phase. Coming to the data set. So the data, there's three different kinds of data that is involved in the study. The first is the video gameplay data, which is just video recordings of the different games played by the 30 players. So each player was made to play for 9 minutes, and the images which were obtained from the videos, it was obtained by splicing the videos every second. So a total of 16,200 frames were obtained. But due to time constraints and because of the manual human resource limitations that we had, only 113 of the frames were annotated for the object recognition task, for the preliminary object recognition task. And during this HCI study, we also collected 30 survey forms. So this was done on Google Forms. And the trajectory data from the HCI study. So initially, for the first 25 participants, trajectory data was not collected. It was only for the last 5 participants that we realized that this was also another form of data that we could use for the study. So trajectory data files consist of JSON, is a JSON file consisting of features such as the position and orientation of the agent and human at different time steps. And for a 2-minute game, approximately 804 time steps of data were present. So a total of 16,080 time steps of data was available for the self-organizing map to train on. So this is just of all of the considerations we took into account when we did the HCI study. So 30 participants were recruited via email, and they were made to play the game on Zoom or on Google Meet, or they were made to play it in person. And a maximum of 2 computer systems were required to get the necessary data. And none of the identifiables of the participants were collected, and all levels of players, both beginner and intermediate, were recruited for the study. We also wanted to recruit expert players, but we couldn't really find expert players. So that's why there are these 2 levels. And a video data of 9 minutes was collected from each player. And in order to evaluate the study, basically the game recordings were manually looked at, and different strategies of leading and following were identified from the videos. And the responses from the Google Forms were also evaluated to see if there were any sort of patterns that would help us in the second phase. So in the second phase, first we did an object recognition. So each frame contains some 8 components, and each of these components were annotated in all of the 113 images that were used. And this was trained on the Vision API on GCP. And so GCP allows you to choose models based on what you'd like to optimize for. So we chose a model that optimized for accuracy, and the trained model was deployed and then later used for inference on GCP. So the evaluation metrics that were considered for this particular task was precision, recall, F1 score, training time, and cost. So F1 score is preferred because here we have an uneven class distribution, because certain components like onions and plates in the kitchen layout might be more than the other components like the different players. The training time is the total time that was taken to train and deploy the entire model. And we use 24 node hours. So you set node hours, 24 is the cost, and for every hour you use for a node, every hour you use for an instance. So the minimum that you get to use, that you can use for an object recognition model, is 20 node hours. And the cost also for the entire training process was recorded. But however, we felt that object recognition was not probably the best way to identify the factors that contributed to trust. And that's why we came up with the second task of using a self-organizing map. So a self-organizing map is an unsupervised neural network that can basically help you understand how a certain feature affects another feature. So in this case, we used 4 different features. One is score. Apart from that, we also engineered 3 other features. So the first feature, so from the HCI study, we were able to see that most of the participants reported that they were being blocked by the agent on multiple occasions, and this kind of led to lesser trust between them and the agent. So we thought that this was a good feature that had to be engineered in our task. So that was one of the features. The other 2 are the number of soups plated by the agent and by the human. So the significance of this is, if the human is plating more number of soups, it's like the human doesn't trust the agent well enough to do the final task of plating the soup and getting points. So these are the 3 different features that we used. And to evaluate this model, we use quantization error and blocking ratio. So quantization error basically measures the quality of the SOM. So an SOM models the data. So it basically shows how accurately you're modeling the data in comparison to the data points. So the blocking ratio is the number of times the agent blocks the human during the entire game versus the number of soups that are served at the serving window. So the entire project was mainly done in Python, and these are the different Python libraries that we used. And as a cloud platform, we used GCP, and we used the $300 free tier. So in the spring semester, originally we thought of using the object recognition module to investigate the factors that motivated trust. But when we felt that this was not an appropriate task, it didn't seem relevant to host this as a web application. So it was only deployed on GCP, and inference was done there. Coming to the design considerations, for the HCI study, we assumed that 30 participants were enough to get a large enough data set for our tasks, and that 113 frames would be enough to train the AutoML object recognizer. And constraints include not including many non-functional requirements such as fault tolerance and scalability. And because we're planning to use the free tier, because we were planning to use the free tier of GCP, we had only a fixed amount of credits to run our experiments, and the number of participants were also restricted. So the system environment, the entire object recognition model was developed on GCP, and all the exploratory data analysis and the self-organizing map was developed locally on a Jupyter notebook. Coming to the risks, so both in the product and business domain, any incorrect assumptions from this study might misguide future research work and might even cause a huge monetary loss to companies that use this work for their projects. So these are some risks. Some challenges that we faced during this project was it was unexpected that our IRB wouldn't be approved. So we had to change our course of action and our plan according to that. And we had to make sure that the participants were attentively answering all the questions. And the annotation of the image data for the object recognition task, that required a lot of manual work. So it's actually probably a useful thing to make this a more automatic process. So this could be a future work also. And object recognition was not an app task. So we had to think of other tasks that might help in this project. And the trajectory data that was used, it didn't contain certain information like whether it didn't contain information of the objects that the players were not holding. So because of that, certain leader and follower patterns could not be evaluated. Coming to the HCI study results, so we realized a few insights from the HCI results. So if suppose a human player begins the game as a leader, and then in the second game, it transitions to become a follower, then we can say that trust exists in this case. And similarly, if a human player starts as a follower and then ends up as a follower, then also we can say trust exists, because the human player would have played with the leader, would have played with the agent, and would have felt that the agent strategy is robust enough to score better points. But however, if the human player starts as a follower or a leader and ends up as a leader, we can't draw any definite conclusions from this, because one, this is just for 2 games. We'd have to see a series of games to actually understand the trend and see if the human player is actually trusting the agent or not. And so in that case, we can't really make a definite conclusion. These are some charts we got from the a survey study that we did. So most of our participants were beginners, and initially when we showed them the gameplay of the 3 different agents and then asked them which agent would suit them, most of them said that they preferred to play with the human aware agent over the other 2 agents. And all of the participants wanted to have get a higher score and did not really care that much about the entertainment aspect. And this is a general trend of the score. So the median score is 100. So for a 2-minute game, most players scored 100. So initially, before they played the game and they were asked if they were going to follow the agent or lead the agent, most of the people wanted to lead the agent and use their own strategy. But towards after playing 3 games, when they were about to play their final game, almost 70% of the participants decided to take on the role of a follower. So that kind of indicates that over a number of games, the human player is starting to trust the agent more and more. So coming to the object recognition results, so we can see that for a very small data set of 113 images, we get a decent F1 score of 0.9076, but the training time is 3.5 hours. And this was a costly, this is the cost for both training and for storing the data set on GCP. But if you notice, for game length and serving window, the performance is very low. So when this was further inspected, it was seen that some of the game length objects were incorrectly annotated. So this kind of shows that manual annotation is erroneous, and we have to really find a better method for that. And the serving window also has a very low performance. This is probably because the serving window is gray and the outside background was white, and it's probably not able to accurately identify, distinguish between these two. So coming to the self-organizing map result, this is the self-organizing map for the 4 different features that we used. So from the legend, you can see that in a self-organizing map, the blue area basically indicates smaller values for that particular feature, and the red area indicates larger values. So if the black and green stars are different data points in the space, then the black data point, which is the black star, has a higher score. And similarly, in that region, we can see that it has a lower blocking ratio, and it has higher number of soups served by humans and higher number of soups served by the agent. So we can see that there is an inverse relationship between score and blocking. Similarly, you can see the same for the green star, where there is a low score and high blocking. A similar trend can also be seen when we plot the scores versus blocking ratio separately. And we can see that as the blocking ratio increases, the score decreases. Of course, there are a few exceptions, but I feel that as we use more and more gameplay data, we'd be able to see a strict decreasing trend. And to see the quantization error, a very low quantization error of 0.1023 was obtained. So the SOM is pretty good. So a final conclusion to this would be the results that we obtained from the qualitative and quantitative analysis. So from the qualitative study, we can say that the more number of games that a human player plays, the more likely it is for the human to trust the agent. And from the survey, it was also seen that blocking of the human player by the agent is a huge factor that decreases score and also degrades trust. And this particular insight was used in our quantitative study. And it was also proved by our SOM, which showed that this was actually true. This trend was there. And when it comes to score and trust, the decision of trusting or not trusting is made over the score in a series of games. So the human player actually decides whether or not to trust the agent based on the score it obtains over a number of games. And that is also one of the results that we see in the quantitative study, because we say that factors that promote score are likely to promote or demote trust, depending on which strategy favors better scoring. So score and trust is very related. So the final 2 inference points that we can make from both of the studies is a player who has played more number of games is likely to trust the agent more, and factors that affect score, like blocking, number of soups, and number of soups plated by either of the players, affect trust. Coming to the future scope. So there's a lot of future scope in this particular project. So one of the reasons why we couldn't train a traditional ML model to predict whether the human player is following or leading is because proper leader follower patterns could not be annotated on this data, as there's very less trajectory data, very few features in the trajectory data. So features about whether there are objects present on the counter outside the outer circuit in the counter circuit kitchen. We don't know that. We don't get that information from the trajectory data. So it might be useful to refine the trajectory data. And another very useful tool, I think, is to develop a frame against trajectory data mapping tool, which maps each frame of the video recording data to each time step in the trajectory. And this might even help train multimodal ML models, which can leverage both image and trajectory modalities. Coming to the reflection, we had weekly team meetings, and we used to brainstorm ideas and solutions to all of the tasks and document all of the progress that was made. And this is just a quick gist of the different tasks that we had done this semester. And I'd like to take this opportunity to thank Professor Stamper and Stephen Moore for all their constructive feedback. Thank you. And any questions?
Thanks. John?
Yeah, good job. Yeah, I wonder, just to ask you on like follow up, how do you think it would differ if you had two humans playing and you didn't tell them, like they thought they were playing with an agent, but it was with two humans? Do you think they would play differently? You're muted. I can't hear you.
I think in that case, there would be more trust, because we are used to the fact of interacting with other human people in a day-to-day life scenario. So I feel in that case, they'd still they'd automatically try to trust. So instead of leading.
Yeah, no, but if they didn't know, what if you told it? What if they thought it was an agent? What if they thought it was an agent?
Who would probably lead or follow? So I feel there'll be more trust in that case.
But what if they thought it was an agent?
Oh, do you mean if they thought that the other player was an agent?
Yeah.
Oh, okay.
Yeah.
Okay. In that case, yes. When the human player would be misguided, they might be more likely to still try to lead. So both of the human players might try to lead, and that might cause other issues. So I mean, that is a good experiment we could try. So that could also come into the future scope.
That's all I have.
Are there any other questions or comments?
Many countries can already quantify this. What do you metrics to say? Is not just is that in numbers? Really quantify
It's generally from the it's more like insights that we're trying to say, that from the visualization that we can see that trust, that when we in the HCI study, when we spoke to the participants, they were saying that one of the reasons why they were following or they were leading is because they're able to score more. So we can definitely mention that trust and scoring is they are related. So in that case, if score is trust, then we can say that blocking, when there's more blocking, there is when there's less blocking, there is more score, and therefore there is trust.
And there's more blocking than human.
Yeah.
This question with respect to the you said you got 0.9 and 113 frames.
Mm-hmm.
Yeah, what should be that metrics are it? Is it the train test, train set, valve set?
That is for the val set. Yeah.
How does 120 models in repetition set?
It was split into 80, 10, and 10.
Isn't that a very small? Like,
Yeah, there,
it's biased. So out of 10, like, if there's a good chance it can. But isn't that a biased method?
yeah, actually that is a bias metric, but by then we had identified that object recognition is probably not relevant to this task. So we didn't really focus on making a larger data set and annotating and fixing. Mhm.
This one more thing, I mean, self-organizing maps, it's really on this big moving measure. It's an unsupervised apartment,
Mhm.
right? So, couldn't models like K-means or KNN, those kind of models.
So-
we use?
Yeah, they could have been used in this case, but the reason why I initially thought of using self-organizing maps was because I thought I'd be able to make so many more features from the trajectory data that I got. And for SOMs, basically they work better for high dimensional data sets.
Use PCL.
Yeah, so that is also a better, that could also have been done in this case.
And like, since these are maps, I just see this as a graph.
Hmm.
Could you have built this as graphs and use the graph?
I never
Okay.
thought of that. Yes.
And listen, I learned something new because I didn't know what S1 is.